The full retrographic microscopy has one limitation, which is the time of the reconstruction. It takes very long. It takes about like 30 minutes to reconstruct one image. But that is the reason we apply the deep learning in here to reconstruct the image only a few seconds. So first of all, I want to introduce like the basic idea about the transport intensity equations. The camera only give us the image of the intensity image. So we in this technique we take multiple images along the x-axis to convert into the phase image, which represents the topography of the information of the sample. For example, I put multiple setup with the different kind of sample, the optical sample, a diamond or the sapphire, and I apply it also on the biological cell. So in order to take the multiple image, I have to move the camera. The 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 limits of the moving camera is introduced in the errors when we apply the application when recon, reconstruction. So in order to overpass this limitation, I put the tunable lens in here. So the purpose of the putting lens in here to introduce the spherical phase, which is I can capture multiple images at a different distance without moving the camera. So I so I just want to introduce very quick about this methods. And this is the setup I put in the lab. So the sample here, I only measure on the optical sample or the biomedical sample, but it's going to be applied to a lot of sample like the eye sample, and you want me to interesting. So in order to verify our result, we want to compare multiple methods together to verify the topography information between digital holography and the TIE. So imagine we want to verify the phase of the eye sample. We put into the setup and we measure the topographical phase based on the computational imaging. So that's one technique. And the other technique is digital holographic microscopy. The basic idea for digital holographic microscopy is to base on the interference of the two same plane wave. One is going to the sample and another one goes directly to the camera at the reference beam. So this is the image I capture in the camera, and this is the without the object, and this is for the object, and apply some kind of pre-processing step to convert into the Fourier transform and crop the image and put it back into the spatial domain. So basically, the digital holographic microscopy can produce a very nice image of the face of the object. However, the traditional setup of the digital holographic microscopy always have the spherical aberrations of the sample that need to be cancelled out in here. So the phase aberration have to be cancelled out. Usually we do the manual segmentation for the background and do the zero-key fitting to get the phase. I'm so sorry, I forgot. So, however, to do the manual segmentation is very take time and require a lot of time for the experts to do the fitting. In here, we introduce another technique called segmentation, auto segmentation based on the deep learning. The first one, the image capture from the previous setup and put it back into the Fourier transform and get the phase out. This is the phase aberration you see, which is similar to the result before. In here, we apply the convolutional neural network to segment out where is the sample and where is the background. And from that, we apply altogether to get the phase aberration and subtract to the original phase image and get very nice result for the background blank and the sample. So why phase operations is the most important part in the digital holography? Because from here, if without the cancellation, the both of cell here present for the same cell. If we don't do the correct phase operation, we're gonna get very incorrect result. The phase of the same cell have to be the same, and it have low feature, middle feature, and the high feature along the model. The first features, they only understand the image by the S, the horizontal and vertical S, and the middle layer, the model can be understand the image with more complicated feature. At the end, with higher feature, and based on this feature, they can understand what type of image is. So this is the concept of the convolutional model understand image by many features. Few cells in the one field of view, but it had high resolution. However, in this technique for tychography microscopy, we use the LED array to illuminate the sample with multiple illumination, which it can give us very high field of view and high resolution. The concept is very simple by taking the low field of view, the low full transform of the low resolution sample, put it back into the wider full transform and do the iteration many times and get the phase and the intensity of the image. So this is the concept by rotating the LED and get many low resolution image and convert back into the high very resolution. So in here I want to introduce the concept of the deep learning, and I want to apply this one into my work for reconstruction instead of using the traditional construction. The first one is the image. The image we want to understand image in many features, and we put it back into the convolutional neural network model. This model will be understand the image by many features, and it have low feature, middle feature, and the high feature along the model. The first features, they only understand the image by the S, the horizontal and vertical S, and the middle layer, the model can be understand the image with more complicated feature. At the end, with higher feature, and based on this feature, they can understand what type of image is. So this is the concept of the convolutional model understand image by many features. So that's why the deep learning have a lot of important application in many fields like classifications for detection, segmentation for the street in medical field. For example, here is to understanding what the object behind the wall, or even transfer the grayscale into the color image, or enhance resolution, transfer the cosmic image into some kind of very useful information, segmentation the satellite image, and recognize the neighborhood, or or classify the state of star. So, the deep learning come into that play. I want to use the deep learning to reconstruct the image from the intensity image. The setup I have to use mainly in this works, which is using the one of the LED array and illuminate the sample in multiple angle and collect the data. So basically, the camera going collect the bright field and the dark field of the image, and with a very high field of view. For this one, it contains about 3,000 cells, bright field and dark field, and I will randomly cropping very small area and put in the convolutional model, convolutional neural network model, and train it. So the process of the deep learning, it look like the same as the outbrain. It can be understand by starting at the first level and understand the image. Like we saw a solution, we find it wrong, and we compare to the another solution, and we find how far we are from the correct, and we learn it again. So this is the process here. It repeat many iterations and until it get the final answer. And the training process, it happen only one time. but later on we can apply to many of the data, and it's gonna be converged and understandable to give us the right answer. So the input of the model is the intensity image X, and we can produce very nice face image, which is very important to detect the light. So this is the model I have used in my work. The first model is converts the intensity image into the free image, and the output of the what I predict here come back into another model, and we can predict this image is phase or not. Both of this model is trained along together and produce very high resolution. So the one of the criteria in the Europa Render for the microscopy is that like the microscopy cannot go less than 1 micron for the resolution. But in our case, we definitely beat that. So our resolution around 300 micrometer. For one of the reconstruction is like 25. Traditional one take 25 minutes, but in we only use 1/10 of the number of the input to produce the image in 8 seconds. And this is some kind of pattern, different pattern we want to use for different scenario. The best one we get a very nice results, which is use the 9 bright field and 20 dark field for J model. The prediction varies in the small area in the whole field of view, and we use the alpha blending together, and we get the near to the gigapixel. Okay, so this is the results. For this model, we have very high result, but one of the benefits thing using the convolutional neural networks is we have no noise at all in this image, and this phase we can detect the thickness of the cell or any sample we want to measure. And in the Fourier domain, we have very broadband, very wider Fourier transform due to the higher frequency we can reconstruct. And this is the table of the some kind of measurement line means absolute errors, noise, structures, similarity of Fourier measurements, and the time. So the total time iteration is 20 minutes, but we reconstruct for the whole field view in 25 seconds. So this is a very quick video. We reconstruct the sample in the real time. Yeah, in here we have like in 3,400 images, and the left hand side is the traditional, and the right hand side is the traditional reconstruction, and the left hand side is what we use for the machine learning to predict. So we see very high resolutions. It is a zoom out for 4 reasons. Okay, and we apply to another type of cell using the what we
Okay.
have been trained.
I'm sorry, we're gonna have to stop there.
Oh, sure, yeah.
Sorry, we're out of time.
Okay, so this is the last one for the focusing using the model. And thank you for listening. Thank you so much.
Thank you, Kang.